Does anybody have homework questions to go over today? For the most part, your quizzes look really good, and you should see your grade in Canvas. I did have some concerns for some of you. I'd like all of you who didn't do as well as you would have liked to be going to the study group each week or meeting with the tutors one-on-one. Okay, it's still early enough in the semester where if you didn't do as well as you would have liked on your first quiz, you can catch up. If you wait till after the second quiz, it's going to be much harder. So everybody who didn't do well, which there weren't that many, but if you didn't do well, please be going to the study group on a weekly basis or meeting the tutors or myself. Remember, you can have Skype tutoring too if you're online. Well, we've been looking at chapter 3. We started talking about the sizes of sets last week. In 3.2, we move on to infinite sets. So we have in the first question here a couple of infinite sets mentioned. So the author says, how much bigger is the set of rational numbers than the set of natural numbers? So remember, the rational numbers are fractions, or any number that can be written as a fraction, actually. And there was always another rational number between any two rational numbers. So anytime we had a rational number and another rational number, there was always one more in between those two. That's not true with the natural numbers. Remember, those are the positive integers. So if you look at the positive integers 2 and 3, there's not another number in between those. And yet, with the rational numbers, if you had 2/3 and 1/2, you could find another fraction in between those two. So this is a question that we will be looking at later on in the section. We'll come back to that. So in 3.2, we're looking at infinite sets, and we're going to remember our protocol for comparing set sizes. Does anybody remember what we said at the end of section 3.1 that tells us if we can tell if two sets are the same size? Does anyone remember that? Yes?
Two sets are exactly the same size if and only if their elements can be put into a one-to-one pairing.
Perfect. Thank you. Two sets are exactly the same size if and only if their elements can be put into a one-to-one pairing. A one-to-one pairing or a one-to-one correspondence. This phrase, if and only if, is used in math in particular to mean that if the phrase that comes before the left side of the if and only if is true. So if this phrase we'll call A is true, if A is true, the phrase before the if and only if, then the phrase after the if and only if is true, B. And the if and only if goes the other way as well. So if the phrase B is true, if their elements can be put into a one-to-one pairing, then two sets are exactly the same size. So that's what the if and only if means when we're talking about logical statements in math. Well, we start small, always. We want a good understanding of finite before we move on to infinite. So let's take a look at finite sets. What is the smallest possible, what is the smallest possible number of elements in a set? What is the smallest possible number of elements in a set? Okay, how about you and your BFF? Do you make up a set together? Yeah, 2. Okay, 2. How about you by yourself? Do you make up a set? You can. You can have a set with just one element. Are there any smaller sets than just one element? Yes. You can have the empty set. How many of you have heard of the empty set? One of your earlier math classes, maybe? Okay, so you could have had an empty set. So the smallest number of elements in a set is 0. So let's look at some examples of finite sets. And then we'll come up with a definition so that we can say, oh yeah, that's why these sets are finite. So who can give me an example of a finite set? We looked at a number in class on Friday, but you could, of course, make up your own. It doesn't have to be one of those. Who can give me an example of a finite set? Anybody want to share? Okay, everybody put out your name placards and then I'll start calling on people, okay? So put your name placard out, please. And then we'll, I can see some of you know the answers and you're just being quiet. All right. Tanner, would you mind giving us an example of a finite set, please?
Markers in the classroom?
Sure. Number of markers, the markers in the classroom. Okay, so that's a great example of a finite set. How about anybody else? Anybody else want to give us another example? Either from your notes or you can make one up. Anna, what do you think? Do you have any?
People in the room.
People in the room? Okay, great. So now we have quite a few examples of finite sets. We'll go ahead and write out a definition. A non-empty set is finite if there is a natural number n such that there is a one-to-one pairing between the set and the set 1, 2, 3, 4, comma, dot, 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 comma, n. A one-to-one pairing between the set and the set 1, 2, 3, 4, comma, dot, 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 comma, n. So let's think of a finite set. by the way, the non-empty set has 0 elements, and 0 is not a natural number. So that's why it's set off from these others in the definition. So this empty set is a finite set, but it has 0 elements, so that's why it's not described along with these others with the natural numbers, because 0 is not a natural number. Okay, so let's pick out a set. How about if we just take the alphabet, part of the alphabet, we'll do A, B, C, D, E, F, G, H, I. And we want to know if that's a finite set. And of course you're looking at it and you're like, duh, of course it's a finite set. But again, we're understanding simple things deeply, and so we're going to make this one-to-one pairing that we talked about on Friday. So let's make a set that we can make a one-to-one pairing with the letters A through I here. So we'd have 1 go with A, 2 go with B, 3, 4, 5, 6, 7, 8, 9. And then we would indicate that pairing with that double-sided arrow that we had. So when you're making your one-to-one pairing, you can make your arrows go wherever you want. You could have A go with 9 and I go with 1, and rearrange your arrows how you like. It's just a little easier to make the one-to-one pairing straight up and down. So we could have our definition met now. We see that the letters A through I are a finite set because we can pair them with the set of numbers 1 through 9. So the end there was 9. So we always want to be able to go back to our definition. I'll just remind you that the natural numbers are the positive integers. So we've been listing them 1, 2, 3, 4, comma, dot, dot, dot. So when we're looking for a finite set, we're looking for one of the natural numbers to make a set 1 through that natural number and pair up the elements in the finite set with those numbers in a one-to-one pairing. Okay, that will let us make a definition of an infinite set. So we had to come up with a definition of a finite set to use to make a definition of an infinite set. So let's do that now. A non-empty set that is not finite a non-empty set that is not finite is infinite. A non-empty set that is not finite is infinite. Okay, so we have to have some elements there. The set can't be empty. And there can't be one of these natural numbers. There can't be a number from this list of natural numbers that we can make a one-to-one pairing with the set. What are some examples? What are some examples of infinite sets? Anybody have any ideas of what might be some examples of infinite sets? We've talked about a few in class. We haven't. We didn't have our definition of an infinite set though. So when we talked about them, we just kind of said, "Oh yeah, and that goes on forever." So what are the things? Some of the things that we talked about that went on forever? No problem. What are some of the things that we put dot, dot, dots after, indicating they did not stop? Yes?
A repeating number?
Yeah, a repeating number. So if we took a number like 2/3, that can be written as 0.66666 dot dot dot, the digits in there make up an infinite set. Good. So you have an infinite set of sixes there. So an infinite set of sixes that I can't come to the end of the list of. Where else did we end up with some dot dot dots going on, or some other infinite sets that come to mind? You know somebody's watching the video of this going, say this. No, they probably not. They probably won't. Maybe they will. All right, so how about the last thing we wrote today that had a dot, dot, dot? The natural numbers. Who thinks the natural numbers are infinite, a set of infinite, a set that's infinite? Yes, okay. Anybody else think that? A few hands. Okay, good. Let's check and see. So it's got a dot, 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 so that looks promising. Let's prove the set of natural numbers. Let's prove the set of natural numbers is infinite. Sometimes the set of natural numbers is abbreviated with the n with a double bar. We'll be doing that quite a bit in this class, okay? So the natural numbers can be abbreviated with a capital N with a double bar. Okay, so what we're going to do, I think this is an example in Wiley Plus. What we're going to do is we're going to think about when your nephew comes up to you saying, Auntie Joe, I found the most biggest, humongous number there is. What are you going to say to your nephew when he does that? So what's your nephew doing? He's assuming that there is a largest number. We'll call it n instead of the most biggest, humongous, gigantic number ever. Okay, and what are you going to do? You're going to pat your nephew on the head and say, yes, Sonny, but what about, and what will you say? Yes.
Add 1 to that number.
Yes. What do you get when you add 1 to that number? So that's what our proof is going to do as well. But n plus 1 is larger. And that is a contradiction. So we have another proof by contradiction now. So the assumption that there is a largest natural number is wrong. Okay, so assume that there is a largest number n. I should say largest natural number because that's what we're looking at. Largest natural number. But n plus 1 is larger, and that's a contradiction. So the assumption that there is a largest natural number is wrong. The set of natural numbers is infinite, just like we would expect. Okay, so we have this set. We have this infinite set. We have the set 1, 2, 3, 4, 5, 6, dot, 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 the set of natural numbers. I could just label it double bar n so that we get used to naming the natural numbers n. And now I'm going to give you another set. Okay, so here's a set. 2, 3, 4, 5, 6, 7, comma, dot, dot, dot. In fact, it's the natural numbers without the first number 1. So, I'd like you to decide. Well, first you tell me this is still infinite, right? The whole dot, dot, dot thing is telling us this goes on and on forever. So there are two infinite sets. But which of these is bigger? We'll call this set A. This always makes me think of this Wodehouse joke. Did anybody ever read a book by P.J. Wodehouse? He's just was a real humorous writer, writing around the 1950s from England. He's just hilarious. So he grows up in England where you have a little bit different terminology than we do in the States, right? So for example, your trunk is your boot, your elevator is a lift, things like that. So in England, what do they call the young lad in the home? Okay, so you have Mr. and Mrs. and you have the young lad. What do you call the lad? Like the young lady would be Miss. What do you call the young man? You call him Master. Okay. So here's what Wodehouse wrote. He wrote, let me get this right. Who is bigger, Mr. Bigger or Mrs. Bigger? Mrs. Bigger, because she became bigger. Okay. All right, you can groan. Okay, now let's next one. Who is bigger, Mr. Bigger or Master Bigger? Master Bigger, because he was a little bigger. Okay. All right, now you're all going to go out and buy those books, right? Anyway, we're going to talk about which is bigger, A or N, and so I'd like you to work on that in your groups. I'd like you to discuss it and decide which is a bigger set. Okay. So Clay, do you mind turning around and writing?
Could be wrong, but
Yeah. Okay. You're just going to go to the floor, okay? Yes, but better. What did you decide?
not sure. It's like maybe thinking the first one's bigger because it has the one in front of it, and that one doesn't, and it does have the dot dot dot. And I was saying that the two's there's going to be a one on there.
Okay, so I can see where you. Okay, good. And how about this?
Probably wrong. I actually said A because since it starts at 2, it's always going to be one bigger.
So it's always got one more.
Yeah. Yeah.
Okay, great. And what is you? Says that one, so it's that extra number in it. Okay. I didn't get around to everybody's group, but it's getting quiet. So I thought you maybe were done with your discussion. So I'll summarize some of what I heard. I heard that the n, the natural numbers, has that extra number 1 in it. So that makes it bigger. And I also heard that this group, this set A is infinite, and the set n is infinite, and infinite is infinite, and so they must be the same size because they're both infinite. Did anybody have any other ideas that came up in their groups that I didn't get to here? Okay, well, when we're not sure, we always go back to our definition. Where did my definition go? Two sets are exactly the same size if and only if their elements can be put into a one-to-one pairing. So let's look for a one-to-one pairing, okay? Did any group try a one-to-one pairing? Anybody that I didn't get to try a one-to-one pairing? Okay, let's try that. All right. Okay, so what if we pair the 1 with the 2 with the 3 with the 4 with the 5 with the 6 with the 7, and then we ask ourselves, is this a one-to-one pairing? And we'll put a little dot because this pairing pattern's going on. Can you tell the pattern now? What would the number down here say 10? What would that go with over in this group?
11.
Yeah, 11. Yeah. Okay. Okay, so you can see what pairing's going on. So let's see if this is a one-to-one pairing. Let's write a question mark. Are any elements missed? Are any elements missed? Are any elements from the set N or the set A not paired with a number from the other set? Anybody see any that got missed? Okay, done or missed? Done or missed? None are missed. Are any used twice? Or more than once? Okay, did any of the numbers get paired, not really paired, but used to go with more than one number? No. So it turns out that the set A and the set N are the same size. Okay. Now, if you were in the infinite is infinite group, you still have to show the pairing, okay? Because it turns out that that's not always the case. There are more than one size of infinity, and we're going to be seeing that. But in this case, these two sets are the same sizes of infinite because you can put them in a one-to-one correspondence with one another. So remember how we did that with, I'll show you this all the time through this chapter, right? We have a one-to-one pairing. Each element from one set put in one-to-one correspondence with each element of the other, just like my fingers on my left and right hand. They're the same number of fingers on each set. So that's kind of weird. I mean, it's totally understandable where you would think, well, this has an extra number. And yet, what holds true with your life history and what you remember throughout childhood, that if you have so many pens and you take away one pen, then you have less pens. With infinite, that's not necessarily the case. With infinite, as long as you can make a one-to-one pairing, then you have sets that are the same size, even though it appears that this set N is bigger than set A. So the answer here is neither. They're the same size. A and N are the same size. We call that cardinality. They have the same cardinality. So when we say the same cardinality, we can think of that as the same size, but size has other connotations, so we use cardinality with sets. So we'd say set A has the same cardinality as the natural numbers. The cardinality of A is the same as the cardinality of N. And since we all know what N is, we can picture it. We can picture that A has the same cardinality. Let's try another set. Let's compare two sets. Call them evens and odds. And guess what they'll be? Evens, 2, 4, 6, 8, dot, dot, dot. And odds, 1, 3, 5, 7, dot, dot, dot. Okay, evens and odds. So are the set E and O the same size? Are the set E and O the same size? Anybody want to venture? Yes, no, or cannot be determined? Yes. Which is yes. Good. Yes. And how would you set up a one-to-one pairing?
The arrows in the 2, 1, 4, 3, 6, 5, 7.
Good. Good. So you can set up a one-to-one pairing, and so you can say, yes, they are the same size. That one's a little easier to see, right? Because it's like, well, sure, like half of the natural numbers and the other half of the natural numbers. So how about we make one that's a little harder to see? How about the set of evens, 2, 4, 6, 8, 10, dot, 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 and the set of natural numbers? Can you decide if those are the same size? Sets. Decide if the evens, 2, 4, 6, 8, 10, dot, 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 and the set of natural numbers, if those are the same size sets. Now it might look kind of like, of course not, because the evens, you've lost half of the set of the natural numbers. And yet, they are both infinite sets. So if we can set up a one-to-one pairing where none are missed or none are used twice, we'll have shown that they are the same size sets. Okay, so with that in mind, what do you think? Same size? Yes, no, or cannot tell? Anybody? Yeah, I see some heads nodding. Okay, yes. They are, in fact, the same size sets because you can set up a one-to-one pairing. And all of these examples are examples that I would expect you to do on a quiz, to take two infinite sets and set up a one-to-one pairing by indicating your double arrows here. So we have a one-to-one pairing, and so these two sets are the same size. None are used twice, none are missed. None of the elements are used twice, none of the elements are missed. They all have a little arrow going to them. Well, I'll give you a set, okay? I'll take the natural numbers and a set we'll call 3 times n. So 3 times n is the set of multiples of 3. So it's the numbers 3, 6, 9, 12, 15, 18, comma, dot, dot, dot. Are they the same size? Okay, if they are, indicate that with a one-to-one pairing. So at your desk, can you please make a one-to-one pairing if possible? So go ahead and make a one-to-one pairing if possible. And if not, then say that's impossible. Was anyone able to make a one-to-one pairing? Okay. And what did you do? Michaela, are you able to share what you did? Okay, what did you do? Thank you. Okay, so that's great. One-to-one pairing, none are missed now. I can always see what's going to go with what, even in the future down the line here to the right. And none are missed, and none are used twice. Good. Anybody else use that pairing? Anybody else use that pairing? Yeah? Okay, good. Okay. Well, you folks are doing very good. This is not easy when you first think about it, because you think, well, this is only a third the size of the natural numbers. But no, it turns out to be, in fact, the same cardinality, the same size sets. How about, oh, I know another set. How about the integers? The integers are sometimes abbreviated with a Z with a double bar. Does anyone remember what the integers are? What set of numbers those are? Anybody want to tell? Okay, I bet you knew it. I bet you had it on your 3x5 cards, and you're like, well, if you hadn't collected my 3x5 cards, yeah, I would have that at my fingertips. Okay, so the integers were the whole numbers. So dot, 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 -3, -2, -1, 0, 1, 2, 3. So the integers go on forever in both directions. They go to the left forever and to the right forever. So let's compare that with n. And see if they are the same size or not. See if they're the same size or not. So this is harder, so I'll ask you to work in a group, okay? And put your minds together and see what you can work out here. Okay, so you're putting that shot. Okay. So what if you rearrange things? Could you rearrange it so that you could still not miss any and still like order them in a different way? Okay, good. You're thinking about how you can match up. You can
Because I guess the natural numbers always keep going because of the ease. So I guess like, I don't know, maybe not right here what we're looking at when we compare, but if like more is like kept adding numbers, we just like double these numbers.
Yeah.
So I like all the negatives and zero. So I think my fraction is what she was using.
So like that first try is not going to work. But if you rearrange, then you can match them up if you figure out a way to rearrange the bigger, one that appears bigger, so that none are missed. Did anybody think you think they're the same size? Because they're both infinite? But there are different sizes of them. We're going to see that. So the question then becomes, yeah. So you have to, there is a way to do it. Let's see if anybody's, okay. So we're still working on this. I appreciate walking around and seeing how you are working on this and thinking it through. So it appears like there's a problem because these go on infinitely to the left. So even if you match up the -3 with the 1 and the -2 with the 2 and the -1 with the 3, there's still -4, -5, -6, and so on, all of these over here on the left. So what we need is a way to order these. Let's order the natural numbers vertically, like that. And then let's work on the integers vertically as well. So we need a way to order the integers so that none are missed. Yes?
Could you do like 0 and then 1 and then -1 and then 2 and then -2?
That's perfect. Good job. That's exactly what we needed. Yep. And if you didn't think outside the box to find that, I don't think I did right away either. I think it took quite a while. So yes, that's a way that you can order those integers so that none are missed. None are missed and none are used twice. So basically it came down to finding a way to list the integers so that the ... is just on the end, but none are missed and none are used twice. Because now that you have them lined up, you can have the 1 go with the 0, the 2 go with the 1, 3 go with -1. Sometimes you can figure out the actual arithmetic to go with this. For example, here on Wiley, we would say each natural number goes with 3 times the natural number. You'll see that notation in this section on Wiley. This one would be harder to do that. I'm not sure there is a pattern. But it's okay, because you can see from the pattern that you've started that you are listing all of the integers without missing any or using any twice. So far, all these sets, all these infinite sets, have a cardinality of n. The natural numbers. So far, all these infinite sets we've looked at have the same cardinality, the cardinality n of the infinite sets. Is there an infinite bigger than the cardinality of n? What does it mean to have a cardinality greater than the cardinality of n? It's like I'm giving you several sets that look smaller, several sets that were infinite but look smaller than the cardinality of n. And now I give you a set that looks bigger than the cardinality of n, and yet it turned out to be able to be put in a one-to-one correspondence with n. N is, in fact, a kind of a benchmark infinite size. So we can all picture this numbers 1, 2, 3, 4, 5, etc. We can picture that set, and so when we can put another set into a one-to-one correspondence with it, we can picture, okay, that's the size it is. So far, n has been our benchmark. Can anybody offer any suggestions of sets that might be larger? What set might have a cardinality larger than n? Anything come to mind that might be? Well, to have the same cardinality as n means they can the elements can be listed. It means the elements can be listed, okay? Because that's what a list is, right? You number a list 1, 2, 3, 4, and so on. We're going to have an infinite set whose elements can be listed, then it will be the same size as the natural numbers. So let's look at another prospect. Let's look at the one the author suggested at the beginning. How much bigger is the set of rational numbers than the set of natural numbers. So that's another suggestion. Remember, every time we looked at the rational numbers, those are the numbers that can be written as fractions, we could find another fraction between any two rational numbers. And if we had found a number in between those two, we could find another number yet again. We could find infinite numbers between every two rational numbers. So let's consider that. So the rational numbers are often abbreviated with a double-barred Q for quotient. The rational numbers then are all the numbers that can be written as A over B, and we've done this quite a bit now. All the numbers A over B, where B is not 0, and A and B are integers. So A and B are whole numbers, but B is not 0. So those are our rational numbers. And we want to know, does that set have the same cardinality as the natural numbers? In other words, can we list it? Can we list it? Okay, so this is going to take a big sheet of paper, so you need at least probably, maybe you could fit it on a half if you write small. But a full page or a quarter of a page would be better, because we're going to work at listing all the rational numbers. So we're going to start with 0. Remember, 0 you can write as 0 over 1, so 0 is a rational number. And then we're going to make a column of fractions whose top or numerator is 1. So I'm going to have 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. And I'll put a dot, dot, dot. So that's all the fractions whose numerator is 1. So 1/100th is way up there, 1/1000th, way, way up there. Now I'm going to write a column with all the fractions whose numerator is 2. So I have 2 over 1, 2 over 2, 2 over 3, 2 over 4, 2 over 5, dot, dot, dot. So there's no fraction whose numerator is 2 that's not on that list. So 2 over 1,000,000, way, way up there, but it's on my list. Now I'll start all the fractions who have a numerator of 3, 3 over 1, 3 over 2, 3 over 3, 3 over 4, 3 over 5, dot, dot, dot. So we're just making a column now to go with each possible integer in the numerator. So my next column will have 4s in the numerator. This is part of your class activity too. So if you haven't been keeping up, catch up, okay? 4 over 2, 4 over 3, 4 over 4, 4 over 5, dot, dot, dot. Are you getting the pattern? What would come next? Yeah, 5s, yeah. Okay, so you get the pattern. So let's put dot, dot, dots over to here to the right as well. So this is a chart that lists all the fractions that are positive. For example, if you wanted to look for 100 over 101, 100 over 101 would be 100 columns to the right and 101 rows up. 1,000,000 over 1,000,001 would be 1,000,000 columns to the right and 1,000,001 columns, 1,000,001 rows up. So we have all the positive fractions. Now let's list all the negative fractions in the lower left quadrant the same way. So first I'll make a column with all the negative fractions with a 1 in the numerator. So I have negative 1 over 1, negative 1 over 2, negative 1 over 3, negative 1 over 4. And now all the fractions with a negative 2 in the numerator. Negative 2 over 1, negative 2 over 2, negative 2 over 3, negative 2 over 4, negative 2 over 5, and dot, dot, dot. Negative 3 over 1, negative 3 over 2, negative 3 over 3, negative 3 over 4, negative 3 over 5, dot, dot, dot. And I think you're getting the idea now, so I'm going to put dot, dot, dots to the left. And we have every single fraction there is listed in on our page here. There's actually a problem with this list, though. So I'd like you to think about this list between now and Wednesday and see if you can tell me the problem with my list, okay? And then on Wednesday we'll finish this looking at the rational numbers and answer our question about how big this set of rational numbers is. I'll see you on Wednesday. So we didn't finish our class activity for today, but we'll get it on Wednesday.